Okay, so day 2 of the series, day 3, or lesson 3. We're doing comparison tests, and this is the second comparison test. It's not our last test, though. There's also a ratio test and a root test and an alternating series test. There's more to come. We'll just do it in chunks. So LCT, first of all, the two series must be different. Okay, you can't compare two things that are the same and call that comparing. Okay. Also, this is similar to yesterday. You need summands that yield positive terms. So somebody asked me, what does that mean, Mr. Shore? I don't know what that really means. It just means that you should not have a summand like this one, -1 to the n squared plus 3n over n cubed plus 4n. Okay, you don't want to use the LCT on this problem because some of the terms are negative. In fact, every other one is a negative term, you see. So don't use it on that. You also don't want to use it on this thing. You don't want to use the LCT on that because that right there has some negative terms, doesn't it? I wouldn't say every other one, but quite often we get negatives for the summand. So this is called the summand. Okay, so it's just not the right test for this. We will see other better tests for those later as we increase our repertoire of skills. But if you have a series with positive summands, you can use the LCT. And just make sure that the limit, when you choose your b sub n, the limit of a sub n over b sub n is positive and finite. I'll have to erase this in a minute, so make sure you write that. And make sure that it is a series, make sure you've picked a series b sub n you already know converges or diverges. So like the DCT, you're trying to pick a familiar series, not just a random series. Pick a G series or pick a P series or something. Okay. A couple hints for picking a valid second series. I gave you hints for this yesterday too. Definitely make sure that you know the convergence or divergence of b sub n before you choose it. And pick something that grows at the same rate as a sub n. We've done that before, okay? For example, if I gave you two functions back in the last chapter, give me 1 second. These two functions grow at the same rate. You can actually tell by looking at them. Maybe it doesn't pop out at you right away, but imagine just looking at large values of x, right? Look at this x. It's big, but not as big as x cubed is, right? What does this reduce to? X to the 3 halves, right? And then if you ignore the 5 on this problem, what do you have? Oh, I wrote this backwards, sorry. I meant to put the 3 here. Let me fix this. And this is just a regular square root, sorry. But if you ignore the x on this one, you get x to 3 halves. If you ignore the x on this one, you get x to the 3 halves, exactly. So these two grow at the same rate. You understand? Okay, so we can do the same kind of thing with series, right? You would want to pick a b sub n that you believe grows at the same rate as the a sub n I gave you see. And if they grow at the same rate, then they behave the same way. That's the idea. It's really simple, okay? You're going to be doing a limit as n goes to infinity. Remember how you proved that f and g grow at the same rate? It was something like this back at 8.3. Didn't you go like this and show me that this was positive and finite? Then you said, therefore, f and g grow at the same rate. How many of you remember doing this last chapter? You put the two functions in the limit. You do limit as x goes to infinity. If you get like 1 or 5 or 3 or e or pi, that means that they grow at the same rate. Well, it means the same thing for series. Series are functions with a positive integer domain. So you should be able to do this with a n and b n just the way you did with f and g, you see. So that's exactly what we're going to do. We're going to try to pick a b sub n that we believe grows at the same rate. We'll show that the limit is positive and finite. This means that functions behave the same way, or the series I mean. Okay, so first example. Can you think of a simpler function that grows at the same rate as 1 over 2x plus 5? I want something that grows at the same rate. it's got to have exactly 1 power of n on the bottom more than it does on top. So what would you choose? You could choose 1 over 2n. You could choose 1 over n. As long as it has the same degrees, you know? Bottom degree 1, top nothing. Okay, great. So we're going to choose let sigma n equals 1 to infinity b sub n be the series 1 over 2n, or you can pick 1 over n. It doesn't really matter. I think I would rather pick 1 over n, come to think of it, because I actually have studied that series before. Haven't I? Doesn't this have a name? What's this guy called? Starts with an H. This is our harmonic series, and he is a known, what, divergent or convergent series? He is a known divergent. Okay, something about that movie, The Government Knows Who's Divergent. Okay, this is a known divergent series. It's a harmonic series. So it's a great choice for many reasons. It's known to be divergent, and it matches the degree structure of the one they gave me. So now it's time to put these together. So you're going to do this now, Lim, n goes to infinity. You're going to slap a sub n on top of b sub n, and just run this limit. Outer is numerator, inner is denominator, and this comes out to a half. Beautiful. What have I shown? By getting a positive finite answer, I've proven that a sub n and b sub n behave the same way. Therefore, sigma 1 over 2n plus 5 from 1 to infinity also diverges. Notice that the LCT, when you get a half, all it means is that the series you're studying behaves the way the one you chose behaves. You see? And since we had a known divergent that we chose, this proves that a sub n is also divergent. Okay, the next one. Next one's let sigma n equals 1 to infinity b sub n equals. Now, for this one, I'm actually going to choose the same series I chose last time. It's a known divergent. You might say, well, why are you choosing that? I don't understand. Why are you choosing 1 over n? It looks nothing like sine of 1 over n. You're right. I can't even think of anything that looks like sine of 1 over n. I really can't. But I know that if I put sine of 1 over n over 1 over n, I think I can handle that limit. So I'm choosing it a little bit for a slightly different reason this time. I think I can handle the following, what I'm about to write. If it turns out I can't handle it, I'll go back to the drawing board and choose a different bn. But look at what I'm going to get. This actually doesn't scare me. I know L'Hopital's rule. I've seen this sine blah over blah before, many times. Even last year in Mr. Lynch's class, you saw that. Sine x over x, right? In fact, we can even change the limit from n goes to infinity to change it to what? N goes to 0 from the right. This is an old trick from chapter 2. And now look at it. This isn't scarce at all. This is simple. What is this? 1 is correct. Our conclusion? This is finite and positive. Maybe we should write that, just for note's sake. Finite and positive. Finite and positive. Our conclusion? The series they gave me, the awkward one, sine 1 over n, should behave the same way 1 over n does. But 1 over n is a known divergent. Diverges also. So we're using an old idea from chapter 8, growth rates, and we're working with series instead of functions. This is extremely logical to me, that we would study how they behave relative to each other, and use one to claim the convergence and divergence of the other. That's just good logic, right? Very cool. Let's look at the next one. Oh, the next one's a repeat. Sorry, we can scratch that one out. This is our last example, example 9. example 8. Ooh, this thing's ugly. Now you might be saying, Mr. Shore, I don't see why we need so many tests. You know, I mean, it's good enough to just give us the integral test, right? No, the integral test is only good for certain types of series. Or you might say, give me a DCT, don't give me the LCT, please. Well, I don't think the DCT is real easy to use on this next problem. Okay? I think it's hard. So what I would suggest on this one is that you study end behavior of this function. What would happen if n was extremely large? Only certain things would survive or be important. You see? So let's go ahead and distribute that numerator so we can see the two terms up top very clearly. Okay, so I'm going to have to do a little bit of thinking before I can create a good B sub n on this one. First thing is, I'm going to distribute that top. It's 3 to the n times n plus 3 to the n times 2. And the bottom is 2n cubed plus 4. I haven't chosen a B sub n yet, but it should be something, I believe, behaves the same way when n is large. Well, how does this behave when n is large? Which terms are most influential? Give me one top and one bottom. You always do one top, one bottom. Which one's most influential on top, 3 to the n or 3n times 2? 3n times n, I mean, or 3 to the n times 2? Which is more powerful? Clearly this one wins, right? n is bigger than 2.
Can you not write that as 3n to the n?
Yeah, I shouldn't have said 3n to the n. I meant to say 3n times n.
Okay.
Sorry about that. Do the same thing on the bottom. So pick one. You only get to choose one, and you have to choose one. You're going to have to pick this one to be the more influential term, right? So I think I can pick a very, very good B sub n series. It should resemble that. Okay, so that, after thinking a little bit, I decide to let the B sub n on this problem, I don't know why I wrote B squared. I meant to write B sub n. I'm going to choose this. It's simpler and has the same growth rate as the one they gave me. What is that? 3 to the n times n over 2n cubed. Does that reduce?
Yeah.
3 to the n over 2n squared. Yes. Okay. 3 to the n over 2n squared. Ooh, the only thing I don't like about my B sub n is it's a little complicated. But remember, you're going to put it in limit with the other one. Things are going to cancel out anyway. You're going to put them in ratio. You're going to slap a limit on there. So let's see where it leads us. If it's too complicated, we can always come back and fix it. So here's the LCT in action. N goes to infinity. Old summand over new summand. Outer is numerator, right? Oh, yuck. 2n cubed times n plus 2 times 3 to the n. Yucky. Inner is the denominator. 2n cubed plus 4 times 3 to the n. Ooh, something simplifies. You see it? Good riddance. Wait, this limit isn't very hard. This should say n goes to infinity. Sorry. This isn't very complicated. This is 2n to the 4th plus 4n, numerator. 2n, I messed up somewhere.
You wrote 2n cubed instead of 2n squared.
Because I'm not paying attention. This is a 2n squared.
No, the other
Oh man, you serious? I got so excited about the limit. So this should be a 2n cubed.
Correct.
But the other one was a 2n squared on the bottom. Right there, right?
Yes.
Okay, just fixed this, right? I mean, I could use my cool highlighter. Hold on. I got it. I just fixed that right there. I like green better. Let's do the green highlighter. Ooh, red and yellow ink. Cool. Okay.
Then on the other.
That means this is a n squared right here, correct? Yes, so I get 2n cubed plus 4n squared over 2n cubed plus 4. This is an easy limit. Just look at the degrees. It's basically 2n cubed over 2n cubed. What does this come out to? 1. Okay, when you get a positive infinite result, you realize you chose a great b sub n, which is rewarding. If you get exactly 1, it means you chose the perfect b sub n in my book. Okay? And so now you can state that this is finite and positive. Obviously, 1 is a finite number and positive. And now your conclusion. Therefore, n equals infinity, n plus 2 times 3 to the n over 2n cubed plus 4 is, convergent also? Or divergent also? That's a good question. The b sub n we chose is a little more complicated than usual. I think it's easy to tell if this blue function is divergent or convergent. Look carefully at it. If you don't know what the blue function is going to do, you'll never get what the original one is. So, the one we chose was 3 to the n over 2n squared. Does that diverge or converge? It diverges for a very simple reason. The nth term test. What does the nth term test? Look back at your day 1 notes. What does the nth term test say? If the limit isn't 0, it diverges. Is the limit of the blue series 0? No. No. It's infinite. The top is bigger than the bottom, always. Okay, so this fails to diverge. I'm sorry, this diverges by the nth term test. So we can say that this one behaves the same way, and it diverges also. Or as Mr. Lynch likes to say, also dies. So, I ran out of space, I'm going to write dies. Means diverges. Dies too. Diverges too. Now, if somebody asks you, well, how do you know the blue one diverges? You say, by the nth term test. It doesn't have a limit of 0. And I did forget to write my sigma right here, guys. So I get sloppy sometimes. I forgot to write the little sigma there. Okay. Sorry it's messy, but the idea was to look at sort of the end behavior to develop a good b sub n. Then we actually just went ahead with the argument. At the end, we were struggling a little bit to know if our b sub n is divergent or convergent. And that's important. But it fails to converge by the nth term test. That's day 1 step. So we can say this dies too. Okay? And that's the end of lesson 3 completely. So you guys can actually spend the rest of the period working on the worksheet. I can print it out now, maybe change your mind, maybe you want a hard copy now.
Yeah.
Let me just say something about my worksheet. On this worksheet, I don't say use the DCT on number 1 and use the LCT on number 2. It just simply says use a comparison test, DCT or LCT, to determine convergence. That is totally up to you what you want to use. You can use DCT or LCT. I will say that it's sometimes hard to use DCT because your sentence has to be perfectly true. And if it isn't perfectly true, you have to find where it's true and what's false about it and all that. Whereas the LCT, you don't have to worry as much about that. You can actually get away with less thinking and a little more work on paper. So my go-to here would be the LCT probably, but I'd like you to try some of each, okay? So there's 7 series for you to work on. The last one's interesting and you're going to want to memorize it. After you think you know, then you will want to memorize that one, add it to your grab bag of tools and tricks and facts. Okay, I'm done. Anyone change their mind? They want a hard copy?